Have you ever found yourself gazing up at the night sky, captivated by the shimmering stars? Their twinkling lights seem to flicker and dance across the expanse of space, each one glowing like a tiny beacon in the darkness. They feel alive, don't they? You can't help but wonder, why do they twinkle? What causes that subtle, almost magical flicker that draws our attention time and time again? Is it the stars themselves, or is there something else in play? Tonight, we're about to unravel this mystery together. We're going to take a quiet, peaceful journey through the cosmos, gently exploring the science behind why stars twinkle. And as we do, we'll uncover more than just a simple scientific explanation. We'll discover the beauty and complexity of the universe itself. But before we dive into the twinkling stars, let's take a moment to consider the stars themselves. These incredible celestial bodies, so far away in the vast reaches of space, have fascinated humanity for millennia. They've been the subject of myths, stories, and dreams, guiding explorers, shaping religions, and helping us navigate the unknown. Yet despite their familiarity, they hold a profound mystery that we only begin to understand through science. Stars are not just distant dots of light. They are massive balls of plasma, each one producing energy through a process called nuclear fusion. This process generates the incredible light and heat that powers the stars. As these stars burn, their light travels across vast distances of space, often taking millions or even billions of years to reach us. And when it finally does, we are left to wonder what causes this light to flicker as it reaches our eyes. Imagine standing outside, looking up at the sky on a clear, calm night. The air is crisp, and the stars are scattered like jewels across the inky expanse. The light from these stars seems steady, almost constant, yet as you focus on them, you notice something. They're twinkling. At first, it's subtle, but as you pay closer attention, the flickering becomes more pronounced. One moment, a star might shine brightly, and the next, it seems to dim slightly. The twinkling is inconsistent, as if the stars are sending signals or messages, like they're trying to communicate with us. But what exactly is going on? Could it be that the stars themselves are flickering? Could the light from these faraway giants be unstable? The answer, as it turns out, is much more interesting and tied to a phenomenon that we can't see directly. Stars don't twinkle because of their own instability. Instead, it's the Earth's atmosphere that's responsible. Before we delve deeper, let's take a closer look at the nature of light. We know that light travels incredibly fast, about 186,000 miles per second, or approximately 300,000 kilometers per second. At that speed, light can travel around the entire Earth 7.5 times in a single second. Now picture light traveling from a star that's millions of light years away, traversing this immense distance to reach our eyes. But light doesn't just travel in a straight line. As it moves through space, it interacts with the elements around it, including the Earth's atmosphere. And here, in the atmosphere, we find the secret behind the twinkling stars. The light from the star passes through various layers of air that make up the atmosphere. These layers are made up of gases, moisture, and tiny particles that vary in temperature and density. As light passes through these layers, it bends. This bending process is known as refraction. Refraction occurs when light travels through a medium with a different density, causing it to slow down and change direction. Think of it like looking through a piece of glass or water. As you look through it, objects appear to be in different positions than they really are. In the same way, light from a star is bent by the atmospheric layers, causing it to appear as though the star is flickering or twinkling. But why does the twinkling vary from star to star? Why does one star twinkle more than another? The answer lies in the way light interacts with the atmosphere. When a star is low on the horizon, its light has to pass through a greater thickness of air, meaning there's more atmosphere for the light to bend and distort. This creates a more noticeable twinkling effect. However, stars that are higher up in the sky, closer to the zenith, don't have to pass through as much atmosphere, which means they twinkle less. This atmospheric distortion is what gives the stars their iconic twinkle, and it's something we've all observed, whether consciously or not. It's not that the stars themselves are unstable, it's that the atmosphere here on Earth is always changing, and that change causes the light to appear different as it reaches our eyes. Now, it's important to note that while the twinkling of stars is mesmerizing, it doesn't happen to everything in the night sky. For example, planets do not twinkle the way stars do. Why? The answer lies in the fact that planets appear larger than stars to the naked eye. When you observe a planet, you're seeing a disk of light, which means the atmosphere has a lesser impact on the light's stability. A star, on the other hand, is so far away that it appears as a tiny point of light. As a result, the effect of refraction on the light from stars is much more pronounced, causing that familiar twinkling effect. As we continue our journey into the twinkling mysteries of the night sky, it's important to understand that the twinkling we see from stars is not just a visual effect. It's a window into the nature of our atmosphere and the behavior of light itself. It's a reminder of how interconnected everything is, from the distant stars we gaze at to the air we breathe right here on Earth. But even though we now understand that the twinkling is due to atmospheric refraction, there are still many other questions to consider. For instance, we know that stars twinkle, but why do they appear so much more stable during certain times of the night? And why does the twinkling vary in intensity from one star to another? To answer these questions, we need to look deeper into the science of light and the atmosphere. The Earth's atmosphere is made up of several layers, each with its own characteristics. From the troposphere, where weather happens, to the stratosphere above it, each layer has a different composition and density, which can all affect how light passes through. For example, when the air is warmer, it is less dense, and when it's colder, the air becomes denser. These variations in temperature and pressure cause the air to be unstable, and this instability is what causes the light from stars to bend as it travels through the atmosphere. Interestingly, this bending of light is not a uniform process. It varies based on several factors, including wind currents, humidity, and even the presence of clouds. In fact, if you're lucky enough to catch a star on a clear night without much turbulence in the atmosphere, you might notice that it twinkles less. However, on windy nights, or when there's more moisture in the air, stars will often appear to twinkle much more intensely. But it's not just the stars that give us a glimpse into the nature of light and atmosphere. The planets, while they don't twinkle, offer us a different kind of insight into the night sky. Because planets are closer to us and appear as disks rather than points of light, their light is less affected by the atmosphere. This steadiness makes them look like they're shining in a way that's almost steady and unchanging. Yet even their light is still subject to some of the same atmospheric conditions. On a very clear night, you might notice planets shining brightly with a steady glow, while stars around them twinkle with every passing second. But why, when everything else in the atmosphere seems to change, does light from a distant star still manage to travel to us at all? How is it that light, with all the bending and distortion it undergoes on its journey through the atmosphere, still manages to reach us at the speed of light? This brings us back to the nature of light itself. Light is not just a simple wave or a simple particle, it's both. In physics, we refer to light as a photon, a tiny massless particle that behaves like both a wave and a particle at the same time. This dual nature of light allows it to move through space at incredible speeds, and even though it gets distorted by our atmosphere, it still manages to carry information about the stars, planets, and galaxies from billions of light years away. This ability of light to travel across such vast distances and maintain its integrity is truly one of the wonders of the universe. As we continue to unravel the mystery of twinkling stars, it's important to note that stars themselves are not constant. They are dynamic, living objects. Stars go through cycles of growth and change. Some stars, known as variable stars, change their brightness over time due to internal processes, such as the pulsations of their core or the fusion of heavier elements. But these stars aren't responsible for the twinkling effect that we see from Earth. The twinkling we see is a result of Earth's atmosphere, not the star itself. This brings us into a fascinating aspect of the twinkling stars. How does the distance between us and the stars affect the way we perceive their light? The farther a star is, the smaller the point of light we see. It's like trying to see a small light on a distant hill. It appears as a tiny dot in the distance, and any slight fluctuation in its light becomes more noticeable. The closer a star is, the more spread out its light appears to us, and the less noticeable the twinkling becomes. It's the very distance that magnifies the effect of refraction. A closer object may still twinkle, but not nearly as much because the light has a broader source. A distant star, however, appears as a pinpoint, making the atmospheric distortion seem much more dramatic. The same principle also applies to how we perceive the brightness of stars. When stars appear closer to the horizon, their light travels through more of the atmosphere, which causes more refraction. The light bends in different directions, making the star appear to flicker. But when stars are higher in the sky, their light passes through less of the atmosphere, so the effect is less pronounced. But what happens when stars don't twinkle? Can stars actually remain steady in the night sky? The answer is yes, but it's a rare occurrence. Sometimes, when the atmosphere is calm and there's little turbulence, the light from distant stars can appear incredibly steady, almost as if the stars are no longer twinkling at all. But these moments are fleeting. Even the most stable stars will twinkle when the atmosphere shifts, when wind picks up, or when clouds move in. The ever-changing nature of the atmosphere ensures that no star's light will ever be entirely constant, even if the star itself remains steady. So we see that twinkling stars aren't just a visual spectacle, they're a direct consequence of the atmosphere's conditions, the nature of light, and the distance between us and the stars themselves. This cosmic dance between light, air, and distance is an ever-present reminder of the vastness and beauty of the universe. And as we continue to explore this mystery, we'll dive even deeper into how different weather patterns, altitudes, and air pressure all come together to create the twinkling effect we observe. Have you ever looked up at the night sky and marveled at the brilliance of the stars? Those little points of light are more than just glowing dots scattered across a dark canvas. They are immense, burning balls of gas, each one producing light and energy through a process that is as ancient as the universe itself. But what exactly is light? How does it travel across the vast distances of space to reach our eyes? And why does it behave in the ways that it does? Light, at its core, is energy. It's the form of energy that our eyes are most attuned to, and it's what makes everything around us visible. But light isn't just the thing that lets us see. It's a force that shapes the very fabric of the universe, influencing everything from the formation of stars to the life cycles of plants. To understand why stars twinkle and how we see them in the night sky, we first need to take a step back and explore the nature of light itself, how it's created, how it travels, and how it interacts with the things it encounters along the way. Light is composed of tiny particles called photons. These photons are massless, incredibly small, and travel at the fastest speed in the universe, 186,000 miles per second, about 300,000 kilometers per second. In just 1 second, light can travel around the entire Earth 7.5 times. This speed is so fast that it can seem almost unimaginable. But despite this incredible speed, light isn't something that can travel through just anything. It needs space to move through, and it travels through vacuum like the empty space in the cosmos without losing its speed. However, when light encounters objects like dust, gas, or atmospheres, its path can be altered in interesting ways. When we look up at the stars, we're seeing the light they emit, which has traveled vast distances through space, sometimes for millions or billions of years. The stars themselves are incredibly far away, yet their light reaches us, despite the obstacles in between. But why does light, even though it travels through such an enormous distance, sometimes appear to flicker or twinkle when it reaches us here on Earth? To answer this question, we need to understand what happens to light when it passes through the Earth's atmosphere. The Earth's atmosphere is made up of several layers of gases, water vapor, and tiny particles. These layers are not uniform. They change in density, temperature, and pressure as you move through them. When light from a star travels through these layers of air, it gets bent, scattered, and distorted. This bending and scattering are what causes the twinkling effect we see in the stars. This process, known as atmospheric refraction, happens because light changes speed as it moves through different mediums. When light passes through the Earth's atmosphere, which is made up of layers of air with varying densities, the light bends slightly. This bending causes the light to appear to shift in brightness, making stars look like they are flickering or twinkling. The effect is especially noticeable when stars are low on the horizon, as their light has to travel through more of the Earth's atmosphere, encountering more layers and thus being refracted more. It's important to understand that this twinkling is not because the star itself is unstable or flickering. Instead, it's due to the unstable layers of the atmosphere that cause the light to appear distorted. The stars themselves are emitting light steadily, but it's the air between us and the stars that causes the effect we observe as twinkling. But how does light travel across these vast distances in the first place? How does it journey from the farthest reaches of space, traveling through the vacuum, and then make its way through the Earth's atmosphere to reach our eyes? The journey of light starts at the core of a star, where nuclear fusion occurs. Inside a star, the process of fusion takes place, where lighter elements like hydrogen are fused together under immense heat and pressure to form heavier elements, releasing vast amounts of energy in the process. This energy, in the form of light, is emitted from the star and travels outward, moving at the speed of light. The energy we see as light from the star has traveled for millions of years before it finally reaches Earth, a journey that spans not just space, but also time. The process of light traveling across space is not an instantaneous one. Light has to traverse the vast distances of the cosmos, distances that are so immense that they're measured in light years, which is the distance that light can travel in 1 year. 1 light year equals about 5.88 trillion miles. Some stars, like our very own sun, are relatively close to us, just 8 light minutes away. But many stars we see twinkling in the night sky are much farther, some being hundreds of thousands or even millions of light years away. For example, the star Sirius, the brightest star in the night sky, is about 8.6 light years from Earth. This means that the light we see from Sirius tonight actually left the star over 8 years ago. When we look at distant stars, we're not actually seeing them as they are now. We're seeing them as they were when their light first began its journey toward Earth. In this way, looking at stars is a little like looking back in time, catching glimpses of their past. The farther a star is, the older the light we see. This brings us to another fascinating aspect of stars: their lifetime. Stars are not eternal. They are born, live out their lives, and eventually die. A star's life cycle depends largely on its mass. Massive stars burn through their fuel much faster than smaller stars, and they have much shorter lifespans. The light we see from a star is only a small part of its journey. It's just the end point of a much larger story. Stars go through complex processes of formation, energy production, and eventual death, during which they shed elements and energy that enrich the surrounding space. This, in turn, contributes to the formation of new stars, planets, and even life. As we continue our exploration of why stars twinkle, we need to understand a crucial aspect of the journey light takes to reach us, the atmospheric layers it passes through. The Earth's atmosphere is far from uniform. It's constantly shifting, changing in temperature, moisture, and pressure, and these variations directly affect the light that passes through it. The air near the Earth's surface is denser, filled with gases like nitrogen, oxygen, and traces of other elements, as well as water vapor and particles of dust. As light travels through this atmosphere, it bends and scatters, an effect that depends on the temperature and density of the air it encounters. This phenomenon is called refraction, and it causes the light from stars to twinkle as it reaches our eyes. The process of atmospheric refraction can be broken down into several key elements. First, light travels in straight lines, but when it passes through a medium with varying densities, like the layers of air in the atmosphere, it bends. The higher the contrast in density, the more the light is bent. It's like if you were to look at an object through a glass of water, where the image would appear distorted because the light is refracted or bent by the water. Similarly, as light passes through the Earth's atmosphere, it's bent in different directions, causing the twinkling effect we observe. This effect is especially noticeable when stars are low on the horizon. When you look at a star that's near the horizon, its light has to pass through a larger volume of the Earth's atmosphere. The light bends more significantly because it encounters more air, and the atmosphere's changing densities cause the star's light to flicker. In contrast, stars higher up in the sky pass through less of the atmosphere, and as a result, their light is less distorted, leading to a steadier glow. Another critical factor in this phenomenon is the movement of air in the atmosphere. The air we breathe is not static, it's constantly shifting. When you look at a star, the light that reaches you has traveled through constantly changing pockets of air, some of which may be more turbulent than others. The more turbulent the air, the more pronounced the twinkling effect. On nights when the air is calm, the stars may appear steadier, but on windy or unstable nights, they seem to flicker wildly. So while stars themselves emit a steady, constant stream of light, the atmosphere makes the light appear as though it's flickering. This dynamic interaction between light and air is what creates the visual spectacle we call twinkling. In many ways, the twinkling of stars is a reminder that our view of the universe is always influenced by the environment through which we observe it. The atmosphere, invisible to the naked eye, plays an essential role in shaping how we see the stars above us. But what about those other objects we see in the night sky? Planets? If the twinkling effect is caused by atmospheric refraction, then why don't planets twinkle like stars do? The answer to this question lies in how we perceive light from stars versus planets. While stars are distant points of light, planets appear as disks or small circles in the sky. The difference in apparent size plays a crucial role in how their light interacts with the atmosphere. Since planets are closer to us than stars, their light doesn't pass through as much of the atmosphere. Furthermore, the light from a planet is spread out over a larger area, making it less susceptible to the atmospheric distortion that causes the twinkling effect. The result is that planets appear to shine steadily, while stars, being much farther away, seem to flicker in the night sky. It's not that planets are immune to atmospheric refraction. Rather, their larger size and proximity to Earth minimize its effects. But let's take a closer look at why we can still see the twinkling of stars so clearly. When we look at a star, we're seeing not just the light it emits, but also the path it takes to reach us. The journey of light is far from straightforward, and as it travels through the vacuum of space, it passes through a variety of mediums. Once it reaches our atmosphere, the light is altered, bending, refracting, and scattering along the way. Even the most distant stars, with light that may have traveled billions of years to reach us, are not exempt from this journey. This brings us to another interesting point about light itself. We know that light behaves like both a wave and a particle, a dual nature that gives it unique properties. As a wave, light has both a wavelength and frequency, which determine the color of the light. The longer the wavelength, the redder the light. The shorter the wavelength, the bluer the light. When light from a star travels through Earth's atmosphere, the interaction between light waves and the atmospheric particles can cause the light to scatter in different directions, adding to the effect we perceive as twinkling. This scattering is most prominent with light at the blue end of the spectrum. As light passes through the atmosphere, the shorter wavelengths of light, like blue and violet, are scattered more than the longer wavelengths, like red. This scattering causes the star's light to appear less consistent, as different wavelengths are bent in different directions. The result is a constantly changing view of the star's light, contributing to its flickering appearance. But there's another reason why we see some stars twinkle more than others. Brightness and distance both play a significant role in the twinkling effect. A dimmer star, being farther away, will appear to twinkle more because its light has to travel longer distances through the atmosphere. The light from brighter, closer stars tends to pass through less atmosphere, and as a result, their twinkling is less pronounced. Now let's shift our focus and consider another important factor, the weather. The atmosphere doesn't just cause refraction, it also changes constantly with the weather. On clear, calm nights, the atmosphere is stable and the twinkling effect is more subtle. But on nights when the air is warmer, windier, or more turbulent, the light from stars seems to flicker more dramatically. The more unstable the air, the more noticeable the twinkling becomes. This interaction between the light from the stars and the constantly changing atmosphere adds another layer of complexity to the twinkling effect. Now, as we continue our exploration into the twinkling mystery, let's dive into how the atmospheric layers interact with the light in more detail. It's amazing how much influence Earth's atmosphere has on how we experience light from stars. We see the twinkling not because the stars are inconsistent, but because the atmosphere itself constantly shifts, bends, and distorts the light that reaches us. But let's consider the individual layers of the atmosphere and how each plays its own role in the process. First, the atmosphere is divided into layers, and each layer has a different density, temperature, and pressure. The troposphere, the layer closest to Earth, is where all our weather events occur. It's full of clouds, winds, moisture, and turbulence. As light travels through this layer, it's bent and scattered in various directions, leading to the flickering effect we see when we look at the stars. The air near the ground is denser, and the turbulence within this layer is what makes the light more chaotic and unpredictable. Then there's the stratosphere, which lies above the troposphere. The air in the stratosphere is thinner and more stable, but it still has some effect on the light from stars. In this layer, the temperature increases with altitude, which can lead to temperature inversion, a phenomenon where cold air is trapped beneath warmer air, creating atmospheric instability. This contributes to a more dramatic effect on the light we see from stars, especially when they're close to the horizon. As we move higher in the atmosphere, we reach the mesosphere and the thermosphere, which are even more sparse and thin. Here, the light from stars may pass through more stable layers of air, but the turbulence below still has an effect, causing stars to flicker. The fact that the atmosphere is constantly changing, sometimes with winds, temperature shifts, and moisture levels, means that stars will never shine in exactly the same way. Even if you're staring at the same star night after night, the light will appear slightly different due to the changing conditions of the air we're looking through. But why do stars twinkle so much more than planets? As we discussed earlier, planets are much closer to Earth and appear as larger disks, meaning the light is spread out over a larger area. This minimizes the atmospheric distortion. When we look at a star, it appears as a tiny point of light, so any disturbance or fluctuation in the atmosphere is magnified. The smaller the light source, the more sensitive it is to atmospheric changes. Planets, being larger in the sky, have a steadier light since the atmosphere has a lesser effect on their light as it spreads across a larger area. Now let's take a moment to appreciate how incredible this phenomenon is. Despite the vast distances light travels and the distortions it encounters along the way, stars still manage to send us their light across unimaginable expanses of space. The journey of light from a star to your eyes might take millions of years, and yet, through the magic of atmospheric refraction, we can still see them twinkle. It's like the atmosphere itself is playing a cosmic game with the light from distant stars, bending it and shaping it into a dazzling show for us. But let's go back to our initial question. Why do stars twinkle more when they're low on the horizon? The answer has everything to do with the angle at which we're observing them. When a star is near the horizon, the light has to travel through much more atmosphere, so it gets bent more significantly. The more atmosphere the light has to pass through, the more it gets distorted, making the star appear to flicker. Stars overhead, on the other hand, have to pass through a smaller portion of the atmosphere, and as a result, their light is less refracted and appears steadier. Imagine you're looking at a distant star near the horizon. The light has passed through layers of the Earth's atmosphere, each one with different densities, temperatures, and moisture levels. As it passes through, the light bends, scatters, and refracts, causing the star to appear to shift in brightness, almost as if it's blinking. This effect is most noticeable in the blue and green wavelengths of light. These shorter wavelengths are scattered more easily by the atmosphere, making the twinkling more pronounced. On the other hand, the redder wavelengths, which have longer wavelengths, are less affected by the atmosphere's turbulence. That's why stars appear more red or orange when they are near the horizon. The light is less scattered, and the twinkling effect isn't as strong. The difference in how light behaves based on its wavelength is a beautiful example of how complex the science of light really is. But there's something even more fascinating about the way light interacts with the atmosphere. The weather plays a huge role in the intensity of the twinkling effect. On nights when the air is calm, cool, and still, stars appear more steady, and the twinkling is less noticeable. However, on nights with high winds, cloud cover, or temperature shifts, the light from stars can flicker wildly. This is because these conditions cause the atmosphere to be more turbulent, which in turn causes the light from stars to bend in unpredictable ways. Just like on a windy night, the turbulent air distorts the light in different directions, making the stars appear as if they are constantly changing. If you've ever spent a clear night stargazing, you've probably noticed that some stars twinkle more than others. Why does this happen? The answer lies in both the brightness and the distance of the stars. Brighter stars, which are closer to Earth, tend to twinkle less because their light is less affected by the atmosphere. Distant stars, on the other hand, appear dimmer and are more likely to twinkle because their light has traveled through more atmosphere before reaching us. This leads us to an interesting idea. Why do we see some stars twinkle more intensely than others? The answer is a mix of distance, brightness, and the composition of the atmosphere. Stars that are farther away often appear smaller and dimmer, meaning their light has to travel through a lot more atmosphere before it reaches us, causing more twinkling. Bright stars, on the other hand, may not twinkle as much because their light can overcome the distortions in the atmosphere more easily. So the next time you look up at the stars and see them twinkling, remember, it's not just a random effect. It's a beautiful, intricate dance between light, air, and the universe itself. Stars aren't twinkling because they're unstable or flickering. They're simply responding to the atmospheric conditions that shape how we see them. Each flicker is a subtle reminder of how much the environment around us influences the light that reaches our eyes. It's a gentle cosmic mystery unfolding right before us in the night sky. As we begin to wrap up our journey into the twinkling stars, there's one more aspect of this phenomenon that's worth exploring. How does all of this connect to our daily lives? The science behind the twinkling stars, the bending of light, and the way our atmosphere plays such a crucial role. It's not just academic or theoretical. It's a part of the world we interact with every day, even if we don't realize it. The same principles that govern how light travels through the atmosphere and how it bends when it encounters different layers of air can be seen in everyday life. Have you ever looked through the air above a hot road in the summer and noticed that the heat makes the road appear wavy or distorted? That's another example of light being bent by air at different temperatures and densities. Just like the twinkling of stars, that mirage effect is caused by refraction, a natural phenomenon that happens every day all around us. Light is the medium through which we perceive the world. It allows us to see color, texture, and depth. The way light interacts with our atmosphere shapes the world we live in. It even plays a role in how we navigate our planet. Our atmosphere bends light not just to make stars twinkle, but also to create the blue sky we see during the day. As sunlight passes through the atmosphere, the shorter wavelengths of light, like blue and violet, are scattered much more than the longer wavelengths like red. This scattering of blue light is why the sky appears blue when the sun is overhead. Just like that scattered blue light, the twinkling of stars is a reminder of how light travels through different layers of our atmosphere, bending and shifting as it moves through varying densities. And while we may not think about these processes on a daily basis, they affect everything from how we see the stars to how we experience the world around us. As we close this chapter on the basics of light and stars, take a moment to reflect on the beauty of the universe around you. The stars twinkle not just because of the light they emit, but because of the incredible journey their light makes through the cosmos. The same forces that bend and twist the light from those faraway stars are what allow us to see the world in all its color and complexity. Light is not just a tool for sight, it's the messenger of the universe, carrying the stories of distant stars and galaxies, traveling through space and time to reach us. So the next time you find yourself gazing up at the night sky, remember that the twinkling stars are more than just a beautiful sight. They are a glimpse into the deeper workings of the universe. They are a reminder of the incredible forces that shape the world around us, from the light that journeys across millions of light years to the atmosphere that bends and molds that light into the flickering dance we see before us. It's not magic. It's the beautiful, complex science of light and the universe. Imagine you're standing outside on a crisp, clear night. The stars above you twinkle like scattered diamonds across the vast blackness of the sky, their light flickering with an almost magical rhythm. Every time you look up, it feels as if the stars are putting on a silent show, their light dancing in the atmosphere. It's a beautiful, mesmerizing sight, but what's actually happening when we see that twinkling? Why do the stars appear to flicker like that? And what's behind the science that makes it all possible? The answer lies in the Earth's atmosphere, which plays a crucial role in how we perceive the light from stars. The atmosphere is made up of a mix of gases, water vapor, and particles, each one of which affects light in different ways. As light from a distant star travels through these layers, it interacts with them in ways that cause it to bend, scatter, and distort. This bending of light is what gives us the twinkling effect. Before we go deeper, let's take a moment to appreciate just how vast and complex the Earth's atmosphere is. It's not just a simple layer of air that surrounds our planet. In fact, it's a dynamic, constantly shifting system that changes based on temperature, pressure, and altitude. As light passes through different layers of the atmosphere, it's bent and scattered in ways that affect how we see the stars above. But how exactly does this process work, and what makes the light from stars twinkle in the first place? The Earth's atmosphere is divided into several layers: the troposphere, the stratosphere, the mesosphere, and the thermosphere. The troposphere, where we live, is the lowest layer and is responsible for most of the weather patterns we experience. This layer is full of turbulent, ever-moving air with varying temperatures and humidity. When light from a star enters the troposphere, it encounters all of these fluctuating conditions, causing the light to bend and change direction. This is the primary cause of the twinkling effect. The stratosphere sits above the troposphere, and while it's more stable, it still has an impact on the way light from stars is refracted. Here, the temperature increases with altitude, and the air is thinner, which leads to a slightly different effect on the way light bends. However, the most noticeable refraction happens when light is traveling through the troposphere, where the atmosphere is thickest and most turbulent. As the light travels through these layers, it's constantly bending and scattering in different directions. This distortion is what gives us the twinkling effect we see with stars. It's important to understand that the stars themselves are constant. They don't flicker or change. What's changing is the way their light interacts with our atmosphere. The reason why stars twinkle more when they're low on the horizon is that their light has to pass through a greater thickness of the atmosphere. The more atmosphere the light passes through, the more it bends and scatters, causing a more pronounced twinkling effect. On the other hand, stars that are higher up in the sky pass through less of the atmosphere, so their light is less distorted and appears steadier. This is why stars appear to twinkle more when they are near the horizon than when they are directly overhead. Now, let's dive deeper into why atmospheric refraction happens in the first place. When light passes from one medium to another, for example from space, a vacuum, into the Earth's atmosphere, which is full of air and particles, the light slows down and bends. This bending of light is what we call refraction. The more dense the air, the more the light is bent. This process is similar to how light bends when it passes through glass or water. In the case of the atmosphere, the density of the air changes with altitude. The closer to the Earth's surface, the denser the air is. As light passes through this denser air, it's refracted more. This is why the lower the star is in the sky, the more of the atmosphere its light must pass through. As the light passes through different layers of air, each layer with its own temperature and density, the light is bent in different directions. The effect is like looking through a wavy or distorted lens, causing the star to appear to flicker. Interestingly, the color of the light also plays a role in how it's refracted. Shorter wavelengths of light, like blue and violet, are scattered more easily by the atmosphere than longer wavelengths, like red and yellow. This is why we often see a slight bluish tint to the twinkling stars. The shorter wavelengths are affected more by the atmosphere's turbulence, leading to the flickering effect. But let's take a moment to consider why this effect is so beautiful and mesmerizing. The fact that light from stars is able to travel across such vast distances, sometimes millions or even billions of light years, only to be distorted by the very air we breathe, speaks to the incredible complexity of the universe. It's as though the universe is playing a game with us, showing us a glimpse of the stars, while reminding us that no matter how distant they are still affected by the forces of nature on Earth. Stars twinkle because they are distant points of light, and the Earth's atmosphere acts as a dynamic filter, constantly shifting and bending the light in different ways. The unpredictability of this effect, based on the ever-changing conditions of the atmosphere, is what makes the stars appear to flicker and shine. And as we continue our exploration, we'll dive even deeper into how weather patterns, wind, and altitude all contribute to the twinkling of stars. But before we go further, let's reflect on just how connected we are to the stars above. Every twinkle we see is a reminder that we are looking at the light that has traveled across immense distances, traversing the vastness of space. The light we see today may have started its journey millions of years ago, and it carries with it stories of distant stars, galaxies, and the very nature of the universe itself. So far, we've discussed how the atmosphere plays a pivotal role in shaping our perception of light, particularly when it comes to stars. We know that atmospheric refraction is the primary cause behind the twinkling of stars. But there's much more to it than just the bending of light. In this section, let's dive deeper into why the atmosphere behaves in such a way, and how weather patterns, air pressure, and altitude impact the way we see stars and planets. Weather and light, a dance of nature. It's no secret that the weather plays a huge role in our everyday lives. From the air we breathe to the way light interacts with objects, the atmosphere influences everything. And when it comes to stargazing, the weather can either enhance the beauty of the stars or distort it completely. But why does the weather have such a profound effect on the way light behaves? The Earth's atmosphere is a dynamic, constantly moving system. It's full of air currents, clouds, and storms that affect how light travels through it. On a clear night, when the air is calm and stable, stars can appear to shine steadily. But when the weather shifts, whether through wind, humidity, or cloud cover, the light from stars becomes more distorted and the twinkling effect becomes more pronounced. For example, on a windy night, the turbulent air causes the light from stars to bend more erratically. The movement of air creates pockets of hot and cold air, leading to more scattering and refraction. This results in the familiar flickering effect we associate with stars. In fact, the stronger the wind and the greater the variation in air temperature, the more pronounced the twinkling effect becomes. On nights when the humidity is high, the air is full of moisture, which can affect how light passes through. Water droplets in the air scatter light, causing the twinkling to be even more dramatic. This is especially noticeable when stars are low on the horizon, where the light has to pass through more of the atmosphere. But it's not just the wind and humidity that affect the twinkling. Clouds also play a significant role. On nights with cloud cover, the stars may appear dimmer or even completely hidden. When light encounters clouds, it gets blocked, refracted, or scattered in unpredictable ways. Some clouds, especially thick, low-hanging clouds, can completely obscure our view of the stars. However, even on nights when there are only thin clouds in the sky, the light from stars can be distorted, causing the twinkling effect to become more erratic. But despite the weather's influence on our ability to see stars, the twinkling is still caused by the atmosphere itself. The interaction between light and the layers of air above us continues to be the primary driver behind the flickering, even if weather patterns make the effect more pronounced. Altitude and atmospheric conditions. Another factor that greatly influences the appearance of stars is altitude. Have you ever been up in the mountains on a clear night and noticed that the stars seem to shine much brighter and steadier than when you're in the city? This difference is due to the thinner atmosphere at higher altitudes. When you're at sea level, the atmosphere is thicker with more air particles, moisture, and dust. As light from stars passes through this dense air, it gets distorted, leading to the twinkling effect we see. However, at higher altitudes, the atmosphere is much thinner with fewer particles to scatter and refract the light. As a result, the light from stars appears more stable and less prone to the twinkling effect. This is why astronomers often set up their observatories at high altitudes, such as on mountain peaks or even in space, where the atmosphere's distortion is minimal. At these altitudes, they can capture clearer, more stable images of stars and other celestial objects. In fact, the clearer the air, the more accurate the data scientists can gather from stargazing and observing distant stars, galaxies, and planets. The connection between altitude and the quality of the view is significant. When you go higher, not only does the air thin out, but you're also above much of the light pollution found in cities. This means the stars shine more brightly, and the twinkling effect becomes less noticeable, offering a more constant view of the night sky. But there's more to it than just altitude. The seasonal changes in the atmosphere also contribute to how we experience the stars. For example, during winter, the air is typically colder and more stable, leading to less atmospheric disturbance. This makes the stars appear more steady and less prone to the flickering effect. On the other hand, in the summer, the air tends to be warmer and more unstable, which can cause the stars to twinkle more. The science of light and color. We've already discussed how the blue light from stars is scattered more than other colors, but let's take a moment to dive deeper into this and understand why this happens. The reason lies in the physics of light waves. Light travels in waves, and the wavelength of the light determines its color. The shorter the wavelength, the bluer the light appears, and the longer the wavelength, the redder it appears. Blue light has a shorter wavelength, which makes it more susceptible to scattering when it passes through the atmosphere. In fact, blue light gets scattered in all directions by the tiny particles in the air, which is why the sky appears blue during the day. When it comes to stars, the blue light is scattered more by the atmosphere, which means it's more likely to be bent and distorted as it reaches our eyes. This is one of the reasons why stars often appear to have a bluish hue when they twinkle. The same phenomenon happens when we see a sunset. As the sun sets, its light passes through more of the atmosphere, causing the blue and green wavelengths to scatter, leaving behind the reds and oranges that we see during a sunset. This gives the sky its warm, colorful glow. But the twinkling stars are a reminder that light isn't as constant as we might think. Even though the stars emit steady light, their light is constantly being modified by the atmosphere. The effect of atmospheric scattering is just one way in which light can be altered as it travels from a distant star to our eyes. As we continue to explore the mysteries behind why stars twinkle, we can't overlook the important role that temperature variations play in the twinkling effect. These variations in temperature in the atmosphere are responsible for creating the air turbulence that bends and distorts the light from stars as it travels toward our eyes. The air near the surface of the Earth is constantly in motion. Warm air rises and cool air sinks. This creates pockets of air that have different temperatures and densities. The constant shifting between hot and cold air masses is what causes the light from distant stars to appear as though it is flickering. As light passes through these pockets of turbulent air, the light is refracted in different directions, causing it to twinkle or flicker. On particularly windy nights, the twinkling of stars can become even more pronounced. Strong winds cause even more air turbulence, creating varying temperatures and densities in the atmosphere. The faster the air moves, the more unstable the air becomes, and this instability creates stronger refraction effects on the light passing through it. The greater the turbulence, the more intense the flickering. So on a windy night, you may find that the stars twinkle more than on a calm, still night. But it's not just about the turbulence created by winds. The temperature of the air also plays a significant role in how much the light is bent. Warm air is less dense than cool air, which means that it refracts light less. In contrast, cool air is denser and refracts light more strongly. The layers of the atmosphere that the light passes through, each with its own temperature and density, change the light's path as it moves, which causes the stars to twinkle. On cold nights, the air near the ground can be particularly dense, which increases the effect of refraction. This makes the stars appear to flicker more brightly. In contrast, on warmer nights, the atmosphere tends to be more stable, and the star's light passes through with less distortion. However, even on the calmest nights, there's always some atmospheric disturbance that causes the light to flicker, though it might be much more subtle. Another aspect of the atmosphere that influences the twinkling of stars is humidity. Humid air, or air that contains more moisture, has different optical properties compared to dry air. Water vapor can scatter light in a similar way to how particles in the air do. This scattering causes the light to lose its sharp focus, leading to the twinkling effect. When the humidity is high, there are more water droplets in the air to scatter the light, causing the stars to appear more distorted and their twinkling more pronounced. As you can see, the atmosphere is not just a still, passive backdrop to the stars. It's an active player in the cosmic drama. The interaction between light and the atmosphere creates a beautiful spectacle that has fascinated humanity for centuries. The twinkling of stars is a complex, dynamic process that reveals the deep interplay between physics, weather, and the natural world. And yet, this phenomenon is just one piece of a much larger puzzle. While the twinkling stars are captivating, they're also a reminder of how much we still have to learn about the universe. We've made tremendous strides in understanding the behavior of light, but there's always more to discover. The fact that the light from stars is traveling through layers of atmospheric turbulence is a humbling reminder of the forces at play on Earth that shape the way we experience the cosmos. Another fascinating element of the twinkling effect is that it is influenced by location. If you've ever noticed how some stars seem to twinkle more than others, or how some stars twinkle more dramatically at certain times of the year, you've witnessed the effect that local weather conditions have on stargazing. For example, in mountainous regions or high-altitude observatories, stars often appear steadier because the air is thinner and there's less atmospheric interference. The lack of turbulent air allows for a clearer, steadier view of the night sky, making the stars seem less prone to the flickering effect. Conversely, in low-lying areas where the atmosphere is denser, the stars tend to twinkle more because their light travels through a greater thickness of air. This geographical effect is another interesting aspect of the twinkling phenomenon. As we climb higher into the atmosphere, the light we see from stars becomes more stable and less distorted by the atmosphere. The clearer the air, the more consistent the light appears. This is why astronomers often build their observatories at high altitudes, where the air is thinner and they can capture clearer, more precise images of stars and planets. In addition to the altitude and geographical location, pollution also has a significant impact on how we see the stars. Light pollution from cities can obscure our view of distant stars, and the artificial lights we see in urban areas scatter light into the atmosphere, causing the stars to appear less sharp. In contrast, when you're far from city lights and the skies are clear, the stars seem much more vibrant, and the twinkling effect is often more pronounced. This is why dark sky locations are prized by astronomers and stargazers alike. They provide the best, most stable view of the night sky. As we continue to explore the connection between light and the atmosphere, it's important to remember that the twinkling of stars is a phenomenon that doesn't just happen to stars. The same basic principles that cause stars to twinkle also affect the way we experience the world around us. The light we see from objects on Earth, whether it's the glow of a streetlight or the light from a distant mountain peak, is also influenced by the atmosphere. Whether you're stargazing or simply walking under the glow of a street lamp, the light around you is constantly being shaped and bent by the atmosphere. Every time you look at a distant object, You're witnessing the interaction between light and the air around you. This complex dance between light and atmosphere creates a beautiful, dynamic world where even the simplest things are subject to the forces of nature. As we draw this chapter to a close, it's essential to reflect on the significance of the twinkling stars and how they remind us of the dynamic nature of the world around us. The flickering effect we see is not a mere quirk of the cosmos. It's a beautiful reminder of the intricate dance between light, atmosphere, and weather. Light from the stars travels across vast distances, yet it is always subject to the unpredictable forces of Earth's atmosphere. By understanding how refraction, scattering, and atmospheric layers influence the way light behaves, we gain insight into the very nature of the universe. We see the stars flickering, not because the stars are unstable, but because the atmosphere, constantly shifting and changing, has the power to alter the path of light, creating a stunning, ever-evolving light show in the sky. In our daily lives, we may take the steady light we see for granted, whether it's the light from the sun during the day or the light from artificial sources at night. We rarely stop to think about the forces that shape how we perceive light. However, the twinkling of stars brings the invisible forces of nature to life in a way that we can see with our own eyes. The process of light traveling through the atmosphere and interacting with its different layers is a cosmic reminder that the universe is never truly still. So the next time you step outside on a clear night and look up at the stars, take a moment to appreciate not just their beauty, but the fascinating science behind their twinkling. Every flicker, every shift in brightness is a result of a complex system at work, one that combines the mystery of the cosmos with the dynamic forces of our planet. In that moment, you're not just witnessing a star, you're witnessing the universe communicating with you, sending light through the vast reaches of space and time, bending and warping as it passes through Earth's atmosphere. Now that we've uncovered the secrets behind the twinkling stars and the atmospheric forces at play, we can carry this understanding into the future. The more we learn about how light behaves and interacts with the Earth's atmosphere, the better we can appreciate the vastness and complexity of the universe. Whether we're gazing at the night sky or simply observing the way light filters through clouds or water, we are constantly surrounded by the incredible power of light. And as we continue our exploration of the cosmos, the twinkling stars will remain a symbol of the beauty, mystery, and complexity that defines our universe. As we continue our journey through the night sky, let's focus on an intriguing question. Why do some stars twinkle more than others? The twinkling of stars is one of the most captivating sights in the night sky. Whether you're an experienced astronomer or simply someone gazing up in wonder, there's something magical about watching stars flicker and shine. But as we've learned, the twinkling isn't caused by the stars themselves. It's the result of the Earth's atmosphere bending and scattering their light. However, not all stars twinkle equally. Some stars seem to flicker wildly, while others shine steadily, almost as though they are immune to the atmospheric turbulence. What makes the difference? The key to understanding why some stars twinkle more than others lies in the physical characteristics of the stars themselves. Stars are not all the same. There are variations in their size, distance, brightness, and temperature, and all of these factors influence how their light interacts with Earth's atmosphere. Let's begin by exploring how the size and distance of a star can impact the amount of twinkling we see. The size and distance of stars are often classified by their size, with some being tiny and others being gigantic. The larger a star, the more its light is spread out, making it less susceptible to atmospheric distortion. This is why giant stars tend to twinkle less than smaller stars. Their light appears steadier because it is less affected by the atmosphere's turbulence. On the other hand, distant stars are often smaller in appearance, which means their light is more concentrated into a small point. When you look at a distant star, it appears as a tiny speck of light in the vastness of space. Because of this small point of light, any atmospheric disturbance has a more pronounced effect, making the star twinkle more intensely. Distance plays a crucial role here. The farther a star is from us, the smaller it appears in the night sky. And because of this small appearance, any fluctuations in the atmosphere, such as changes in air pressure or temperature, become more noticeable. So even though the star itself might be stable, the light reaching our eyes is distorted and flickers as it passes through the atmosphere. This phenomenon is known as stellar scintillation, and it's what causes distant stars to twinkle more. Interestingly, stars that are closer to Earth don't twinkle as much, even if they're large in size. This is because the light from a closer star has a larger point of origin, so the effect of atmospheric disturbances is less noticeable. For example, our own sun, which is very close to us, doesn't twinkle at all. Its light is so steady that we don't see the effects of atmospheric refraction. The brightness of stars. In addition to size and distance, the brightness of a star also plays a role in its twinkling. A brighter star emits more light, which makes its light less affected by atmospheric fluctuations. The more light a star emits, the more resilient it becomes to the distortions caused by the atmosphere. When a star is very bright, the intensity of its light overpowers the small disturbances caused by the atmosphere, and the twinkling effect is less noticeable. On the other hand, dimmer stars are more vulnerable to the distortions caused by the atmosphere. Since they emit less light, even small atmospheric fluctuations can have a larger impact on their appearance. When you look at a faint star, the light is more easily scattered or refracted by the air, causing the star to twinkle more intensely. This is why bright stars like Sirius, which is the brightest star in the night sky, tend to twinkle less compared to fainter stars. The brightness of Sirius makes its light more resilient to atmospheric distortions, so its twinkling effect is less pronounced. In contrast, stars that are fainter or located at greater distances appear much more likely to flicker in the night sky. The temperature of stars. A star's temperature can also influence how much it twinkles. The temperature of a star determines the color of its light. Hotter stars emit bluer light, while cooler stars emit redder light. But how does this affect the twinkling? The answer lies in the way different wavelengths of light interact with the atmosphere. Shorter wavelengths of light, like blue and violet, are scattered more easily by the molecules in the atmosphere. This scattering causes blue light to be redirected in various directions, which makes it more likely to be distorted as it passes through the atmosphere. On the other hand, longer wavelengths of light, like red, are scattered less, which is why stars that emit redder light tend to twinkle less. So, A hot blue star will likely twinkle more than a cool red star, simply because its blue light is scattered more. This is another factor that contributes to the varying intensity of twinkling from star to star. As you look up at the sky, you may notice that blue stars appear to twinkle more intensely than red stars, and this difference is largely due to the way their light interacts with Earth's atmosphere. Why do some stars twinkle less? We've already discussed how distance, size, and brightness influence how much a star twinkles. But what about the stars that seem to twinkle less? What makes them so different from the rest? As we mentioned earlier, giant stars tend to twinkle less because their light is spread over a larger area, making it more resistant to atmospheric distortion. These stars emit massive amounts of energy and have much larger surfaces than smaller stars. As a result, their light is less likely to be scattered by atmospheric particles. Stars like Betelgeuse, a red supergiant, emit large amounts of light, and their sheer size helps their light maintain its stability, making them appear steadier in the night sky. Similarly, close stars that are relatively bright also tend to twinkle less. Their proximity to Earth allows their light to pass through less of the atmosphere, which means the light is less likely to be refracted and scattered. Therefore, stars like Capella, which is one of the closest stars to Earth, tend to shine more steadily than those farther away. The role of location. As we've discussed, atmospheric refraction is the key factor in why stars twinkle, but the location from which you're observing the stars also matters. Altitude and light pollution are two significant factors that influence how we see stars. When you're observing stars from a high altitude, there's less atmosphere to distort the light. That's why some of the world's largest observatories are built on tall mountains, like Mauna Kea in Hawaii. The thinner atmosphere at high altitudes allows stargazers to see the stars more clearly, with less twinkling. Conversely, if you're stargazing from a low-altitude location near sea level, the atmosphere is denser, and the stars may appear to twinkle more. Additionally, light pollution from city lights and artificial sources can significantly impact how we see stars. In areas with high light pollution, stars appear dimmer, and their light is more susceptible to scattering. This means stars may twinkle more or seem to disappear altogether. In places with minimal light pollution, you can see stars more clearly, with less interference from scattered light. This is why stargazing in remote, dark locations provides the best view of the night sky. Now that we've discussed how a star's size, distance, and brightness influence its twinkling effect, let's explore how atmospheric conditions and local geography contribute to this mesmerizing phenomenon. Atmospheric conditions and their role in twinkling. While we've already touched on the fact that the Earth's atmosphere plays a key role in bending and scattering the light from stars, let's dive deeper into how specific atmospheric conditions create the conditions for twinkling. One of the most influential aspects of the atmosphere is air turbulence. Our atmosphere is constantly in motion, with winds, air currents, and shifting temperatures, all contributing to the dynamic nature of how light behaves. This constant movement of air leads to what we call atmospheric turbulence, which is the primary cause of the twinkling effect we see in stars. Think about the last time you were driving on a hot day and looked at the road ahead. Did you notice how the air above the pavement seem to shimmer and distort? This phenomenon, called a heat haze, is another example of how turbulent air can affect light. When the air is heated, it expands and becomes less dense, creating pockets of air with varying temperatures. As light passes through these varying air masses, it bends and scatters, causing the light to distort, much like how the road ahead looks wavy. In the case of stars, this effect is much more pronounced because the light travels across vast distances to reach us. Even slight atmospheric turbulence can cause a significant distortion in the light. When a star's light passes through unstable layers of air, it appears to flicker. The higher the turbulence, the more intense the twinkling becomes. This is why the stars near the horizon appear to twinkle more than stars overhead. The light from horizon stars has to pass through more of the Earth's atmosphere, increasing the likelihood of encountering turbulent air. But turbulence isn't the only atmospheric condition that affects starlight. Temperature also plays a huge role. On nights when the air is warmer, the atmosphere tends to be less stable, and stars appear to twinkle more dramatically. In contrast, when the air is cooler, the atmosphere is generally more stable, and the twinkling effect is less noticeable. This is one reason why stars tend to appear steadier on cold nights. The air is less turbulent, and the light from stars has a smoother path to travel through. Another important factor to consider is humidity. Moisture in the air can scatter light, creating a more pronounced twinkling effect. On humid nights, the light from stars passes through a denser atmosphere filled with water droplets. These droplets scatter the light, making it appear to flicker and dance. On drier nights, the air is less dense, and the stars tend to shine more steadily. The level of moisture in the atmosphere can therefore have a major impact on the visibility and appearance of stars. The influence of local geography. While atmospheric conditions certainly play a big role in the twinkling of stars, the location from which you're observing them also has a significant impact. The higher your altitude, the clearer and steadier the stars appear. Geographical features, like mountains, valleys, and flat plains, can all affect the amount of atmosphere you need to look through in order to see the stars. For example, when you're stargazing at high altitudes, such as on top of a mountain, the air is thinner and contains fewer particles, water vapor, and pollutants. As a result, the light from stars passes through a smaller portion of the atmosphere, and the twinkling effect is much less pronounced. Observatories, like those at Mauna Kea in Hawaii, are built at high altitudes for this very reason. The thinner atmosphere provides a clearer, steadier view of the night sky, allowing astronomers to study stars, planets, and galaxies without the distortion caused by Earth's denser layers of air. Conversely, cities or low-lying areas can experience more atmospheric interference due to higher levels of pollution and moisture. When you're in an area with a lot of light pollution, the twinkling effect may be more difficult to notice. The artificial lights from the city scatter and reflect off the atmosphere, leading to less contrast between the stars and the sky, and making them appear dimmer and more scattered. Additionally, because the air near the ground is denser, light from stars has to pass through a thicker atmosphere, which increases the likelihood of distortion. On the other hand, remote, rural areas with minimal light pollution and clearer air offer the best conditions for stargazing. In these locations, the stars shine brighter and their light is less affected by atmospheric disturbances. The higher the altitude and the fewer the pollutants in the air, the steadier and more stable the stars will appear. In fact, some of the most vivid and beautiful views of stars can be seen in the most remote parts of the world, where there's less interference from the atmosphere. Why we don't see the sun twinkle. We've discussed how the atmosphere causes distant stars to twinkle, but have you ever wondered why the sun doesn't twinkle, despite being much closer to us? The answer lies in the way we perceive the sun's light. Unlike distant stars, the sun is a large disk in the sky, and its light doesn't have the same concentrated point-like quality that stars have. The light from the sun spreads out over a larger area, and as a result, any atmospheric turbulence has a lesser effect on its light. When we look at the sun, its light is diffused, and the twinkling effect isn't noticeable. Additionally, the sun's light is much brighter and more powerful than that of any distant star, so the atmosphere's refraction doesn't alter it as much. This is why the sun appears as a steady, unflickering light, even though it's subject to the same atmospheric conditions as distant stars. The twinkling of stars is really a result of the difference in the way we perceive light from distant objects compared to closer ones. The role of technology in observing twinkling stars. As we continue to explore the science behind why some stars twinkle more than others, it's worth noting how technology has helped us better understand the light from stars. Modern telescopes and imaging technology can correct for atmospheric distortion, allowing astronomers to capture clearer, more detailed images of stars and other celestial bodies. The effect of twinkling is still present, but advanced tools like adaptive optics can adjust for the turbulence in the atmosphere, allowing us to see through it more effectively. These technologies can also help us study how atmospheric conditions affect stargazing and improve our understanding of how light behaves when it passes through different layers of air. Thanks to these innovations, we can get a much clearer and more accurate picture of the night sky, making it easier for scientists to study distant stars and galaxies. How human perception shapes our view of stars. In addition to the physical and atmospheric factors that influence how stars twinkle, there is also a crucial element at play: human perception. Our eyes are incredibly sophisticated, but they aren't perfect. The way we perceive the twinkling of stars is partly due to how light interacts with our retina, the part of the eye that processes incoming light. When light from stars reaches our eyes, it is often dim and scattered by the atmosphere. Our retina, which is sensitive to even the faintest light, has a limited capacity to process this fluctuating light. The tiny changes in brightness that we see are interpreted by our brains as flickers or twinkles. This phenomenon is especially noticeable with dimmer stars, whose light is already weak before it passes through the atmosphere and encounters more distortion. When we observe stars at night, their fluctuating brightness becomes more noticeable because our eyes are more sensitive to small changes in light in low-light conditions. During the day, we are surrounded by much brighter light from the sun, and our pupils are contracted to handle the intense brightness. But at night, the absence of light causes our pupils to dilate, and we become much more sensitive to subtle changes in the intensity of light. This makes the twinkling effect even more pronounced. Interestingly, our brain's visual processing also contributes to our perception of twinkling. It has evolved to detect even the slightest changes in light intensity, which is helpful in dim or uncertain environments. However, when looking at stars, the rapid changes in light intensity caused by atmospheric disturbances are exaggerated by the brain's tendency to focus on contrasts. We are constantly processing the flickers and inconsistencies, and that's why we often see stars as twinkling rather than simply shining steadily. The color and temperature of stars. Another key factor that determines how much a star twinkles is its color and temperature. As we discussed earlier, shorter wavelengths of light, like blue and violet, are more easily scattered by the atmosphere, which leads to the bluer appearance of stars. This scattering effect not only causes the blue wavelengths to twinkle more, but also makes blue stars appear to flicker more than red ones. The temperature of the star plays a big role in this because it determines which wavelengths of light it emits. Hotter stars, like Sirius, have a higher surface temperature, which causes them to emit more blue and violet light. These stars tend to twinkle more dramatically because their light is scattered more by the atmosphere. In contrast, cooler stars like Betelgeuse emit more red and orange wavelengths of light, which are less prone to scattering. This makes red stars appear steadier and less likely to twinkle, so the twinkling you see from a star is also influenced by the spectral type of the star. Stars that emit a higher proportion of blue light will twinkle more noticeably, while stars that emit more red or yellow light will appear more stable. This explains why stars like Sirius, which is a hot blue star, are often seen to flicker more vigorously, while stars like Antares, which is a cooler red giant, twinkle less. The temperature of a star also tells us a lot about its size and behavior. Hot stars burn brightly and burn out faster, while cooler stars tend to live longer, more stable lives. But even though the colors of stars give us clues about their temperature and size, the twinkling of their light has more to do with the interaction of that light with Earth's atmosphere than the star itself. The atmosphere, with its turbulence and temperature variations and changing pressure, is what causes us to see the light from stars flickering in the first place. Why planets don't twinkle like stars? By now, you might be wondering, if stars twinkle because of the atmosphere, why don't planets do the same? After all, planets are in the same sky, under the same atmospheric conditions, so why don't we see them twinkle the way stars do? The answer lies in the size and shape of planets compared to stars. While stars appear as tiny points of light in the sky, planets appear as disks. This difference in appearance plays a crucial role in the twinkling effect. Since planets are closer to Earth and have a larger angular size in the sky, their light is not as easily affected by the atmosphere's turbulence. When you look at a planet, the light from that planet is spread out over a larger area, making it more resistant to atmospheric distortion. The atmosphere may still bend the light slightly, but because the light from a planet is coming from a larger disk, the atmospheric disturbances are less noticeable. This is why planets, like Venus, Mars, and Jupiter, appear to shine steadily compared to stars. In contrast, the light from stars is concentrated into a small point, and because of this, the atmosphere has a more significant impact on the appearance of the light. The more turbulent the atmosphere, the more noticeable the twinkling becomes. For this reason, stars twinkle much more than planets. The role of light pollution. Another crucial factor influencing how we see the stars is light pollution. In cities and urban areas, the night sky is often obscured by artificial lighting. The glow from streetlights, buildings, and billboards scatters through the atmosphere, making it harder to see the stars. Not only does this reduce the visibility of distant stars, but it can also enhance the twinkling effect for the stars that remain visible. Light pollution doesn't just make the stars harder to see, it also changes the way we perceive their twinkling. The extra light in the atmosphere can make stars appear dimmer and more scattered, so even if the atmosphere is clear, the presence of artificial light can make stars seem to flicker more. This is why dark sky locations, far away from city lights, provide the best stargazing experiences. When you are in a place free from light pollution, the stars appear brighter, steadier, and their twinkling becomes much more subtle. The science behind light pollution and twinkling. When light pollution is present, it not only dims the stars but also increases the likelihood that light will be scattered in different directions. The artificial light from cities reflects off particles and molecules in the atmosphere, scattering light in all directions and causing the stars to appear fainter and more scattered. This increased scattering contributes to the twinkling effect. The stars may appear to flicker wildly, not because of the stars themselves, but because of the interference caused by light pollution. Interestingly, the effects of light pollution are often most noticeable when looking at stars near the horizon. As we've discussed earlier, stars that are lower in the sky have to pass through a thicker layer of atmosphere, which increases the effects of refraction and scattering. When light pollution is added to the mix, it amplifies the effect, making stars appear to twinkle even more intensely. This is why stargazing in cities can be a frustrating experience. You may have to work harder to see the stars clearly, and the ones you do see will appear more scattered and flickering. As we near the end of this chapter, let's reflect on the extraordinary beauty and complexity behind the twinkling of stars. We've covered a lot of ground, from the atmospheric layers that refract light to how the brightness, distance, size, and color of stars play crucial roles in the twinkling effect. We've also seen how external factors like weather, altitude, and light pollution influence how stars appear to flicker in the night sky. But in all this, there's one final concept to consider: how this knowledge connects to the larger mystery of the universe. The twinkling of stars isn't just a charming visual effect. It's a reminder of the immense scale of the cosmos and of the natural forces that shape the way we see the universe around us. When we look at the twinkling stars, we're looking at light that has traveled across vast distances, often millions or even billions of light years. That light is not static. It's dynamic and constantly affected by forces beyond our immediate perception. Just as the atmosphere bends and scatters that light as it reaches us, stars themselves are constantly shifting and changing. Some are born, others die, and many more undergo cycles that change their brightness and intensity. The very fact that we can see stars twinkling, despite the distortions caused by the Earth's atmosphere, is a testament to the power and persistence of light itself. Even as it passes through layers of shifting air and turbulence, that light remains constant in its journey from star to observer, and that stability is something we can count on every time we look up at the night sky. Moreover, The twinkling effect serves as a visual representation of the dynamic relationship between light and the environment it travels through. The Earth's atmosphere is constantly changing, and with it, the way we experience the stars. From night to night, and from one location to another, the twinkling of stars can be different, yet always it is the same process at work, the bending, scattering, and refracting of light. Understanding why some stars twinkle more than others allowed us to appreciate the science behind the night sky, but it also deepens our connection to the cosmos. It reminds us that the universe is full of mysteries, yet it is also governed by principles we can observe, measure, and understand. The twinkling stars are a cosmic dance, a complex interplay between light, atmosphere, and human perception, and they give us a glimpse into the nature of the universe itself. So the next time you look up at the sky and notice a star twinkling, take a moment to reflect on the beautiful science that makes it happen. The twinkling of stars is not just a simple optical illusion. It's the result of a remarkable combination of factors, from the movement of the atmosphere to the inherent properties of light. It's a phenomenon that brings the vast and mysterious universe closer to us, right here on Earth, reminding us of the beauty and complexity that surrounds us in every moment. Whether you're gazing at the stars from a high mountain peak, a quiet country road, or the bustling streets of a city, the twinkling stars are a constant reminder of the dynamic, ever-changing nature of the universe. And as we continue to explore the mysteries of the cosmos, we'll keep looking up with a sense of wonder and curiosity, knowing that the stars above us are always telling their story through their flickers and their shine. As we close our exploration of the importance of twinkling stars, it's clear that their significance stretches far beyond their visual effect. Stars have been our guides, symbols, and sources of inspiration for centuries. From ancient navigation to modern astronomy, stars have shaped the way we understand the universe and our place within it. They have been our constant companions, lighting up the night sky with their brilliance and beckoning us to explore further. The twinkling stars represent a connection to the past, to the ancient astronomers, sailors, and storytellers who gazed up in wonder and saw a cosmic order that governed their lives. Cultures around the world have relied on the stars for more than just navigation. They have seen them as divine messengers, as signs from the gods, and as symbols of immortality. The twinkling stars are a reminder that we are part of something much larger than ourselves, a vast, interconnected universe. Today, the twinkling stars continue to inspire and inform. While technology has given us new ways of exploring the cosmos, the magic of the stars remains. Whether through scientific exploration, artistic expression, or spiritual reflection, the stars continue to be a source of curiosity, awe, and wonder. As we move from the twinkling of stars, let's cast our gaze outward to the other celestial bodies that populate our night sky. The universe is home to countless objects that have captured human imagination, but none are as enigmatic as the planets, moons, and distant galaxies. While stars seem to be the constant and steady sources of light, the other objects in the sky offer a different type of beauty, one that defies the twinkling effect. The twinkling of stars occurs because of the way their light travels through Earth's atmosphere, but when we look at planets, the effect is almost non-existent. Planets don't twinkle, They shine with a steady light that remains consistent regardless of the conditions of the atmosphere. Why is this? Stars, as we've learned, are distant, and their light travels across vast distances before reaching us. Because their light is concentrated into a small point, it's more vulnerable to the effects of the atmosphere. Planets, on the other hand, are much closer to Earth, and their light is spread out over a larger area. As a result, their light is less likely to be disrupted by the turbulence in the atmosphere, causing them to appear as steady, non-twinkling points of light. This phenomenon is further explained by the size of planets. While stars appear as tiny points of light, planets appear as larger disks. This makes their light more stable and less susceptible to atmospheric distortion. So when you see a planet like Venus or Jupiter in the night sky, it shines with a steady, almost constant glow, while a distant star might flicker and sparkle. But the stars and planets aren't the only celestial bodies worth studying. There's also the fascinating world of moons, asteroids, and comets, and each with their own unique characteristics and roles in the cosmos. Moons, for example, don't produce their own light, but rather reflect the light of their parent stars. Their surfaces, with all their craters, mountains, and valleys, create fascinating patterns of light and shadow that make them some of the most captivating objects in the sky. Asteroids and comets, on the other hand, are small, icy bodies that travel through space. They don't twinkle like stars or shine steadily like planets, but they create an entirely different kind of spectacle when they pass near Earth. Comets, with their long, glowing tails, streak across the sky, offering a brief but beautiful reminder of the dynamic forces at play in the universe. Let's move on to explore the fascinating world of distant galaxies. These collections of stars, dust, and gas are the building blocks of the universe itself. While we can't observe the individual stars within these galaxies, we can observe the light they emit, light that has traveled across millions or even billions of years to reach us. This light often appears to flicker or twinkle as it passes through Earth's atmosphere, but in reality, it's the atmosphere, not the galaxies, that's responsible for the effect. The study of galaxies has opened up entirely new realms of understanding about the cosmos. Hubble's deep field observations have shown us galaxies that are billions of light years away, providing us with a glimpse into the very beginnings of the universe. These distant galaxies, with their billions of stars, hold the secrets of cosmology, how the universe began, how it's expanding, and what its future holds. But galaxies are not static objects. They're constantly in motion, colliding, merging, and evolving. The Milky Way, our own galaxy, is on a collision course with the Andromeda Galaxy, and in about 4 billion years, the two galaxies will merge to form a single, larger galaxy. The collision of these galaxies will create new stars, planets, and possibly even new life. The study of galaxies helps us understand the dynamic nature of the universe and the forces that shape it. Another fascinating aspect of the universe is the study of black holes, neutron stars, and other extreme objects. These cosmic phenomena represent the limits of physics, where the laws of gravity, quantum mechanics, and relativity collide. Black holes, for instance, are regions of space where gravity is so strong that not even light can escape. These regions of darkness, paradoxically, are some of the most intriguing objects in the universe. Their study has led to groundbreaking discoveries about the nature of space and time. As we continue our journey through the cosmos, let's focus on one of the most fascinating aspects of the universe, space-time. The concept of space-time combines the three dimensions of space with the dimension of time, creating a unified framework that explains the gravitational forces at play in the universe. Einstein's theory of relativity revolutionized our understanding of space-time, showing that the fabric of space-time is curved by massive objects like stars and planets. But how does space-time relate to the twinkling of stars? Well, the atmosphere's effects on light can be thought of as a local distortion in the fabric of space-time. As light travels through Earth's atmosphere, it's bent, refracted, and scattered. This distortion is similar to the way light is bent by the curvature of space-time around massive objects like stars and black holes. In a sense, the twinkling of stars is a miniature example of the complex interactions between light and the fabric of space-time. The study of space-time and the effects of gravity has led to many fascinating discoveries about the universe. For example, gravitational lensing, where light from a distant star is bent by the gravity of an intervening object, creates a magnification effect that allows us to see distant objects in more detail. Similarly, the expansion of the universe, first observed by Edwin Hubble, shows that galaxies are moving away from us, and the further a galaxy is, the faster it's moving. This discovery has profound implications for our understanding of the universe's origins and its future. As we wrap up our exploration of the twinkling stars and the larger celestial bodies that inhabit our universe, we're left with a sense of awe and wonder. The stars and planets, galaxies, and black holes all work together in a delicate and intricate dance that spans across time and space. The twinkling of stars, though an optical illusion created by Earth's atmosphere, is a reminder of the vastness and complexity of the universe. The stars are not just points of light. They are symbols of the mysteries waiting to be unraveled, and they remind us of the never-ending journey of discovery. In our next chapter, we'll dive deeper into the connection between stars and human understanding, examining how the stars have influenced culture, philosophy, and even modern science.